Alright, so now we shall start our discussion of the center of mass. Firstly, we shall define what the center of mass is. We shall define it as a special kind of position vector. We'll start by defining it for an n-particle system, and then we will continue our definition for continuous systems. And finally, we shall see the physical implication of this position vector, what it does when you apply an external force on an extended system, and so on. So first of all, let's consider a system, a well-defined closed system of n particles. We've of course seen this definition before when trying to talk about the momentum of such a system, right? So for a system of n particles, let's suppose we make a choice of coordinates. Remember, the choice of coordinates is entirely up to you. So suppose you select an origin and three axes in three-dimensional space, of course. And suppose that the n particles have position vectors in this coordinate system, which are r1, r2, r3, up to rn, right? We have n particles that constitute this system. Then the center of mass is a vector. It's a position vector that's defined in the following way. We take the sum mi times ri, which is basically, it goes like this, right? m1 r1 plus m2 r2 up to mn rn. And then we divide this sum by the total mass of the system. The total mass of the system, which we write as capital M, is simply the sum of the individual masses, right? This is simply the definition of our center of mass. As you notice, this is of course a position coordinate. So if we complete this evaluation, we will get some point or some position vector RCOM somewhere here perhaps, and it will have the position vector RCOM. Let's look at a few examples. The first one is a very trivial example. Let's try to find the center of mass of a system consisting of a single point particle. Okay, so all this system consists of, it's a well-defined closed system. If you think of it like that, it's just a system with a single particle. So you select an origin and you select axis, that is, you select a coordinate system, and you write down the position vector of this particle in this coordinate system as the vector r. Then using the definition of center of mass, you find that RCOM equal to, well, if you write down the whole definition, it's just the sum MIRI divided by the total mass of the system. But here n is just equal to 1. It's a one particle system. So you just have 1 by m times mr equal to the vector r. Does this make sense? Of course, for a single point particle, it makes sense that the center of mass of this point particle is right at that point itself, right? So for the single particle, RCOM, or the position vector of the center of mass, is the same as the position vector of the particle itself. That makes excellent sense. So now that we have seen the trivial example of the center of mass of a single point particle system, of course, the next thing we consider is the center of mass of a system of two particles, a well-defined closed system of two particles with masses m1 and m2. Of course, the definition of center of mass gives you RCOM equal to 1 over the mass of the whole system, which is just m1 plus m2, into m1r1 plus m2r2. Of course, we have to select a coordinate system first to even talk about the position vectors. We do need to select a coordinate system. So suppose you have this vector r1 and this vector r2, right? To really make sense of what this center of mass means, so far we've only described it as a mathematical object, right? As a definition. But to understand what this is all about, let's think of some special cases. So, special case 1, which is, let's say the two masses that constitute the system are equal, so that you have the two masses m1 and m2. For our convenience, let's take the coordinate system like this. The origin of this coordinate system that we chose is right at the middle of these two particles. Where do you think the center of mass should be? Well, if you have any intuition about center of mass, just from intuition you know that the center of mass in this case, with both of these two masses, and let's say those two masses are both m, it's not hard to imagine that the center of mass should be at some point right in the middle of these two particles, so that in this chosen coordinate system the center of mass should be at the origin, right? That's what we guess. Now let's try to evaluate that mathematically. As you know, by definition the center of mass would be given by 1 over m plus m, the total mass of the system, which is 2m, and then you have m1 r1. But of course r1, the position vector of this first particle, let's say the first particle is this one, this is particle 1, okay? The position vector of the first particle is just xi hat, right? And the position vector of the second particle is minus xi hat. So that you see that the position vector is given by 0. Well, you could probably write this as a vector, it's just 0 I hat. And this is exactly as we expected. So you find that the position vector of the center of mass, right? The center of mass is exactly at the origin as expected. Alright, so case 2. In case 2, we will consider that one of the masses is greater than the other. Let's say m1, this mass at the right, is greater than m2, the mass at the left. So in this case, because when we had both masses equal, our center of mass was exactly in the middle, right? In this instance, where m1 is greater than m2, we should expect that the center of mass will be somewhat displaced towards the heavier mass, right? Let's see if that indeed plays out. So by definition, we have the center of mass, or the position vector of the center of mass, is given by 1 by m1 plus m2, and then you have the m1 times the position vector of the m1 particle, which is xi hat, plus m2 times the position vector of the m2 particle, which is minus xi hat, right? So just to be clear, it's these vectors. You have this vector xi hat, and then again you have this vector, which is minus xi hat. Alright, so but you see, since m1 is greater than m2, if you simplify this, you get RCOM is m1 minus m2 by m1 plus m2 xi hat. But m1 being greater than m2, this quantity, with of course x being a positive number, this quantity is positive. So that means that the center of mass is indeed at the positive x-axis, that is, it's near m1. So the center of mass is closer to the heavier particle, which is exactly as we expected. So let's carry this discussion a bit further. Let's say that m1 is not just greater than m2, it's much greater than m2. So we've tried to draw that using this sort of funny picture here. We have 2 point particles, m1 and m2, but we are saying that m1 has a mass which is much larger than the mass of m2. Can you imagine such a system in real life? Well, one system you can think about is the Earth and Sun system. The mass of the Sun is much larger than the mass of the Earth, right? So in carrying out this discussion, we will have something to say about what is the center of mass of the Earth-Sun system. Where does that lie? Obviously, from our previous case 2, we know that the center of mass lies closer to the Sun than to the Earth. So the question is how much closer? So okay, once again, by definition, for such a two particle system, the center of mass would be given by 1 by m1 plus m2, m1 xi hat minus m2 xi hat. But let's simplify this a bit further. Because m1 is much greater than m2, of course m1 plus m2 would be approximately m1. In other words, m2 doesn't add up much to m1, right? So if you add a million to 1, it's close to a million, something like that, right? In which case m1 divided by m1 plus m2 is approximately m1 by m1, which is 1, right? And then m2 divided by m1 plus m2 is approximately 0, because m1 is just so much greater than m2. If you apply these approximations here, what do you end up with? You end up with RCOM is approximately xi hat. But what's xi hat? Xi hat is, of course, the position vector of the much heavier m1 particle, right? In other words, if one particle is very much heavier than the other particle in the two particle system, the center of mass of this system is approximately right on that particle. So you can imagine that in the Earth-Sun system, the center of mass of the Earth-Sun system is on the Sun, approximately.